If you've ever been in a basic science or physics course, your teacher may have done an experiment originally made by Italian scientist Galileo Galilei in the already leaning Tower of Pisa, throwing from great height two objects, a light one and a heavy one, with the purpose of showing that everything falls at the same time, no matter the weight. But why does this happen? I mean, it kinda feels like heavy things should fall faster, right? First, let's look at it mathematically. Newton told us the force with which two objects are attracted to each other is directly proportional to the product of their masses and inversely proportional to the square of the distance that separates them, which simply means that the attraction force depends on both objects' masses. If they are more massive, there will be more force between them, but the more distance between them, the more will the force decrease by a lot. That same dude in his second law told us an object's acceleration is directly proportional to the force applied to the object and inversely proportional to its mass, which means that the more force you apply to an object, the more it will accelerate. But the same force applied to a heavier object will result in a lower acceleration, but you probably know it as F equals ma. So, if we equate these equations to each other, we see that the force on an object due to gravity will be equal to its mass times its acceleration. We want to know why every object falls at the same time, which is, why does every one of them accelerate in the same way? To solve for A, all we have to do is divide both sides of the equation by the mass of the object to have this new equation. Do you notice something? An object's gravitational acceleration isn't dependent on its own mass. It's nowhere to be found in the equation. It only depends on the mass of the other object and its distance to its center. Okay, so most people hopefully know that the acceleration that we feel on the surface of the Earth is of about 9.81 meters per second squared, sometimes horrendously rounded up to 10, and we can now work that number out using our best friend, Google. Mass of the Earth, 5.9 times 10 to the 24th kilograms. Mean radius of the Earth, 6,071 kilometers, 6,371,000 meters. Remember your units. G? Okay, so far I've ignored the elephant in the room. What the hell is G? Very easy, a nerd will say. It's the universal gravitational constant. And yes, that's it. But what does it mean? Well, you can see it as a measure of how strong gravitational interaction is. It turns out that gravity is the weakest of the four fundamental forces, topic for another video, so its constant is pretty small. Imagine we calculate the acceleration on Earth without this constant. Yeah, no, something went terribly wrong in both value and units. We need something to make it work, and that's what big G is for. Some very smart people have measured its value with an array of experiments, and its value is this. Okay then, let's plug in those values into our equation to get the magical number of 9.81 meters per second squared. Going back, if it's not clear why mathematically all objects fall at the same time if you throw them from the same height, you can also picture it this way. Yes, if you've eaten some extra hamburgers recently, the Earth definitely pulls you stronger. That's why it's harder to lift 40 pounds than 5. You feel the Earth pulling the weight harder, thus it should fall faster. But also, the heavier weight has more resistance to be moved by Earth, a property we call inertia. The more mass an object has, the harder it is to move it. It's like if the Earth said, there is more force between us because you have more mass, but at the same time, it's harder for me to accelerate you because you have more mass. You, on the other hand, pose less resistance to be moved, but there is less force between us, and that's how both fall at the same time. And nerds will say, but relativity, and they will be right. Gravity is more the curvature of spacetime than two objects pulling on each other, but I think it's a good enough approximation to understand it, at least at some basic level. Maybe someday I'll make that video. But in the meantime, if you want to help the creation of more videos like this, you can support me through Patreon, where you can donate whichever amount of money you want, starting at $1, in exchange for perks every time I upload a new video. You obviously don't have to do this, these videos will stay for free for everyone forever, but if you want, and you can, well, please. Thank you very much for staying until the very end. Goodbye.